Thank you so much for checking into this video. It's based on a paper I gave at MARINTEC Senior Forum in Shanghai just in December 2019. But I've adapted it for the RENA website and I made a few changes which I think hopefully will improve some of the technical base of the paper. I hope that you'll find the presentation useful in pulling together the many different strands in the so-called revolution. I think a lot of people are using the word revolution nowadays, which is going on. I chose the title Anatomy of Cargo Transport because it seems to me that this hints very nicely at the fact that we have arms, legs, feet, heads, all sorts of bits of anatomy floating around, and at the moment we need to assemble them into some sort of vehicle which is capable of moving us towards the various goals that we're now facing. And that's the purpose of the paper. The introduction, let's start with the last maritime revolution. And let me say on the side, I'm not going to give a complete talk here. I'm just going to make a few comments on the slides. But the last maritime revolution was very much about sailing ships and the transition to fossil fuels. And it happened 200 years ago, which may seem to you a very long time ago, but I think I'm hoping to prove that there's another side to this. The next cargo transport revolution we're facing, I think, is probably on a similar sort of scale to the wind to steam revolution. But this time we're dealing with digital technology, which is something radically different from what naval architects are used to. And also we're having to find a new generation of fuels to improve the efficiency and reduce the emissions. And that, these are very big challenges. I think the steam revolution did, however, provide us with some very interesting insights about the way that one should manage technical transitions in the maritime industry. And that's really why I want to start off by looking back a bit. It's not just for the sake of history, though the history is great as well. The transition from sail to steam took actually over a century. And in fact, this was after 300 years when the three-masted, square-rigged sailing ship had ruled the waves and had almost single-handedly opened global trade and exploration. This is Captain Cook's endeavour, in fact, an ex-collier. You can see that in the hull. For 300 years, these sailing ships had made it possible to develop trade, and by the 18th century, shipbuilders and naval architects were massively skillful in refining the design. But when steam and iron hulls arrived in the 1790s, really a lot of new questions needed to be answered. And the point to make here is that revolutions don't publish a timetable. People make them happen. That's the reality. If we look at the evolution of the sailing ship, it's quite interesting. The steamship. First one, well, there's a few contenders for the first one, but this is a 60-foot steamboat driven by I think stern-mounted oars, actually, and it ran out of Philadelphia, 1790. It could only go a few miles without breaking down. The Agamemnon, built by Alfred Holt in 1866, was the first really steamship that was really capable of trading globally. It had 60-pound boilers and some sort of variant on the compound engine. And basically, this ship could get to Shanghai from London or from Bristol, wherever it sailed from, Liverpool, to with just one bunker stop in Mauritius, and only used 25% of its capacity for coal. That was the big difference. The previous ships, you couldn't really go anywhere because they used so much coal. You had to go get halfway there and you're going to go and look for bunkers. I think the lesson from this lot is that the evolution required vision, understanding, it required materials, and it required application. That's to say, shipyards capable of building the ship, and it required an entrepreneur. And I think really Alfred Holt pulled all this stuff together. He'd worked in the railways. He knew you could build a high pressure boiler, which was not something that people in the shipbuilding industry knew at that time. And so he did that. If we look at the timeline on this, it's quite interesting. The first steamship, 1790. Evolving steam technology took 70 years, and not much happened. You can see the sailing ship cycle. We really didn't have very many sailing ships by 1860. And then as the technology gelled, the whole thing took off. And then from that point on, it took 50 years to build the fleet. And I think this tells you something about the dynamics of bringing together the complex mix of materials and technology needed to build steamships to build merchant ships that can trade around the world. And I think we should bear that in mind. Interestingly, the first shot at setting up a Naval Architect Association was in 1791. It didn't do very much, but in 1860, RENA was set up, and I think, as they say in one of their publications, after years of waiting, suddenly the answers to technical questions were commercially vital for ship owners and shipbuilders. They wanted the information, they needed it, and I think we're again coming to perhaps a parallel position in the next revolution that occurred in the 1860s for steam. Just before we finish this, a reminder of what we're up against. In 1840, the merchant fleet was in fact entirely green. 30,000 ships carried 20 million tons of trade. You can hardly see it on the axis here. And the shipping industry didn't really move all that much cargo. We moved forward to 2018, and as you can see, diesel engines had come along using oil, and this was a terrific step forward because it's so easy to load and move the oil around the hull, and the diesel engine was clean and compact. So I think that was a very big step forward. And at the same time, diesel engines made it possible for the whole block construction method to be developed for the mass production of very, very big ships. And all of this combined to give us 12 billion tons of cargo in 2018. And so, that's where we were. One can't overstate the importance of the diesel engine and all of this. It burned oil that cost $1 a barrel, and it was so easy to handle. It was so rich in energy, you didn't need much of it. And if we just examine that a little further, this is the Emma Maersk's engine. Thanks to fossil fuels, this engine generates 109,000 horsepower, does the work of about 3 million men, or women, I suppose, working 8-hour shifts. The people powering it need a town like Athens to live in, and they'd eat 9 billion calories a day, 3,000 tons of grain, so you're going to need a handy bulker keeping them served. And every ton of oil produces 3.3 tons of carbon. Fantastic. That's the elephant in the room. And at the MARINTEC session where I gave this paper, Professor Gerhard Strasser, I think, demonstrated with scientific precision the massive problems faced in replacing this beast with something economically and technically in the same league. Well, moving to the future, we've got three major building blocks to contend with. The first is climate change, which has absolutely rocketed to the top of the agenda really in the last 18 months, 2 years since IMO's meeting in 2018. And I think we have to assume that is going to be there. I mean, whatever you may feel, we can't ignore it. Sea trade is facing a rapidly changing era after the emergence of China, which followed Japan, Korea, Europe, and we've had an enormous maturing, really, of the trade flows, and that's going to lead us into a new era for seaborne trade. I think that's very important. So we'll look at that. And the third thing is technology, the information and automation revolution. And I'm going to suggest that actually, just as Alfred Holt was 70 years into the steam revolution, I mean, he built the Agamemnon 60 years after John Fitch's boat, 1791 boat. We're now 70 years into the this particular technology era, and that's something I'm going to expand on in a minute. Let's see how we do all these things. Well, climate change, it's about decarbonising an industry built on fossil fuels. It's not a small change. It's every bit as big a change as the move from sail to steam in the 19th century. IMO sort of set out one of the important pointers because they laid down firm regulations for where we must be in 2050, but I think they hope that we can do much more. And the big problem with this is that the regulatory scenario is very unpredictable, and I think really the smart approach is to move ahead of the game and to really keep one step ahead of the regulators as far as you can. And I think the recent experience with sulfur, with water ballast, have shown how difficult that is. It really is very tricky. Basically, this shows you the whole thing. This is million tons of CO2 emissions on this axis. This is IMO's target for 2050. This is what happens if we just carry on as we have been, growing trade at 3.2% and building ships to do 14 knots. That's where we get to. There are 4 ways to implement IMO's vision and to make it, to close that gap. The first is less cargo, and I'll go into this more in a minute, but I think a lot of people are coming round to the idea that pricing could be very important here. We've got to slow down ships. This has already happened. A lot of the fleet is slow steaming. We also need to fine-tune existing technology because we haven't got anything to replace it with immediately. So we have to do a very good job of slickening up and smartening up today's ships. And we need to design them for the conditions in which they'll be trading. That means slow steaming. The third method is we find zero carbon power. This is very unpredictable. There's a new set of information seems to come out every couple of months on this. I think ammonia seems to be popular at the moment. But the truth is there is no quick and easy solution, basically. The oil was brilliant. Fossil fuels, massively powerful. Apart from nuclear, it's very hard to fill their shoes without paying an awful lot more money. And finally, of course, the one thing we know is all of these things depend on management, and I think that means management of the ships, but also management of shipping companies. Well, let's just quickly run through the scenarios ever so quickly. This is scenario, business as usual scenario. I've already showed you that. The next one is scenario 1, and what we're doing here is we're actually cutting trade growth to 2.2 knots. We're staying at 14 knot speed, but 2.2% per annum cargo growth. And that gets us down, saves us 1.2 billion tonnes of cargo, which is fantastic. So, you know, the cargo scenario is definitely one to take seriously. The next scenario, scenario 2, we cut growth to 2.2% and we slow down to 10 knots. There you go. If we do those, we're down to somewhere, we shave another 0.8 billion tonnes off, a bit more than 0.8 billion tonnes. And so that takes us down to 800,000 tonnes of carbon. And then the third scenario is the one in which here we go, sorry, a bit of trouble with the slides there. Half the fleet has to go to zero carbon because, of course, it's half of 800 by 2040, 50, and we're going to need a lot more ships to do that because the ships are going 10 knots in this scenario, which means you need more than 40% more ships. This is the most difficult technically and in economic terms, and it's very unpredictable. Well, if we add the final thing, which is scenario, which is rethinking management systems, Peter Drucker, who's my favourite guru, he says that only 3 things happen naturally in companies: friction, confusion, and underperformance. Everything else requires leadership. And I think this really is a message that we should very much take to heart. Well, okay, issue 2. Now let's move on to seaborne trade. I've said quite a lot about this in the run-up, but there are 2 goals to the seaborne trade scenario. The first is to ensure that the cargo transport adds value. And what we're doing here is focusing not on the volume of cargo, but of the value. And those are not the same thing. Think about it. Second thing is we want to minimize door-to-door emissions. So we need to put the shipping, sea transport together with the land transport, and we need to be excellent at measuring emissions so that you can say, yes, that consignment took that amount of carbon, and we can measure progress. This is really important. The trade scenario I've shown here is that trade growth, I believe, is the most important variable. Here we are, we're doing 12 billion tonnes today, and there are really 2 questions we should be asking ourselves about managing seaborne trade. The first is question 1. Trade has grown 27% since 2008, since the credit crisis. 27% of what most people in shipping would regard as a lousy decade, frankly. And the question we've got to ask ourselves is, you know, if you can grow trade this fast, maybe we can shrink it this fast without too much loss of value. I mean, it's only 10 years difference in the world. And the second question is, 37% of seaborne trade in 2018 was fossil fuels. So what should we be planning for in 2050? I mean, if the rest of the world does its job, this part of the trade should, you know, diminish very substantially. So I've put up here 7 ways to change trade volumes. I'm not going to burden you with them. You can have a look at the slides, download the slides afterwards and look at them if you're really interested. The important thing about trade is that inland transport has demonstrated the miracles that you can perform with digital information and very big databases. And one of the things we were promised in the shipping industry when containerization arrived was business-to-business deliveries. The image was you pick up the container from the factory and deliver it to the purchaser in another continent. That has never happened. We do quayside to quayside, but I think I don't have to convince you that people like Amazon, Uber, UPS have demonstrated that you can do door to door if you really want to. And a good place to start here is short sea transport, because shipping has much lower emissions than land transport, as you can see in this chart here. This is the emissions in grams. It seems to have disappeared. Sorry about that. This is emissions in grams per ton kilometre, and it's 3 for a big container ship, 6 for a mid-sized tanker, 8 for a small bulk carrier, 80 for a road truck, 435 for air freight. So there's a lot of stuff here, and I think that land transport's now very congested and produces much more CO2 than sea transport. So short sea shipping can be very attractive. I've done the calculations, absolutely possible. You know, we bring 11,000 containers into the south of England every day. I'm sure a lot of those we could save quite a bit of hassle and carbon if we were to do clever transshipment. And I think in this context, B2B short sea transport actually provides a better business environment, but it also provides you with a brilliant testing ground for the new technology. And this moves me on to the short sea systems, because I think that part of the maturing of sea trade after 50 years of headlong globalization is that we are moving towards local maritime clusters. And the focus of trade, these are all big enough areas to support their own economic integration. And so I think we can see that perhaps as we move into the next 50 years, we'll be focusing much more on developing trade within these regions rather than bringing everything from Asia to Europe, Asia to America and back again. And of course, this will be helped by the fact that, as Kernan Nagel said in a recent article in Trade Winds, customers are actually becoming very conscious and willing to pay more for climate-friendly transport. And they believe, Kernan Nagel believes, this is going to be a big thing in the coming years. And so the revolution, I believe, will probably include new short sea trading patterns and should certainly include improved short sea shipping. It's a great way to develop the technology that we have in front of us. The third issue is smart shipping, and I think this is about organization as well as telematics, deep learning, autonomy. They're all part of the same process. Now, I mentioned earlier on the long time it took to develop the steam revolution. Do you remember I said that John Fitch produced the first steamboat in 1790? Well, in fact, interestingly, we have a very close parallel with the computers, because the first commercial computer was built in 1951. 70 years ago. It had 8.75K of memory and an awful lot of wires. By the mid-1960s, we had the CDC Super 600, which had a 10 megahertz clock speed, which was 10 times other machines at the time, and about 980K of memory, and it cost $7 million. And as you can see, lots and lots of tape devices. You had to put the data in with punch cards. I started my life on exactly that machine, actually, working on that. They had one at the University of London Computer Centre. And where we are today is a whole bunch of things, not just big computers. Core i7 processor has 8 cores with 12 megabytes of cache, 3.6 gigahertz of clock speed. You can add as much RAM as you like, really, and $393 from Amazon and it comes in a nice box like that. Not quite like that one, is it? And this is an FPGA, and this is it's for a car, but this is a system which plugs into the car's onboard diagnosis plug, which all cars have. You can get one, and you can buy this system for I think it's $9 a month, and it allows you to monitor what your children are doing in your car at a great distance, how fast they're going, how they're accelerating, etc., etc., and all for $9 a month. Some might say you don't really want to know that, but you know. Would you trust your model with your life? The model we're referring to here is the autonomous model, I have to say, not the other sort of model. And the answer to this, I think, is that you know, there is a vision that, you know, Captain Ronnie the robot will be driving the ships in the not too distant future. But, you know, the people I've spoken to and the lectures I've been to have convinced me that although the people programming these systems test the algorithms very extensively, we are a long, long way from making them secure and safe enough to trust your life with them constantly. I think so we mustn't rely on total automation. What we must do is use it intelligently. And I think the first place to start is that the place where it should all be happening is ships' functional systems. And this is the way, I'm not saying it's the only way, you develop propulsion systems, auxiliary power systems, auxiliary machinery systems, ballast and trim management systems, navigation systems, cargo handling systems, and IT and comms systems, and finally the maintenance systems. Many of these are already under development, but I think the next generation of ships will need really well engineered systems for the areas I've described or something like that. But they will need to talk to each other, and the really crucial thing here is the communication between these systems, because if they can't communicate, rolling out upgrades is going to be a nightmare, and maintaining the systems will be absolutely scary, to be quite honest. And to do that, we need to follow the car industry. The vehicle industry moved into digital networks 30 years ago. In 1967, this car, every switch and component was connected by wires. But in the 80s, the car manufacturers were under massive pressure to develop ways of monitoring car engine performance for the regulators, emissions and things. And they developed in 1983, Intel and Bosch developed the CAN bus backbone that turned cars into computers on wheels. That's what The Economist called them in 2018. And this car here is a computer on wheels. It runs around a CAN bus backbone. It's absolutely packed with electronic equipment, and there are hardly any wires. It's all done and it's massively reliable. And of course, this absolutely opened the way for the all-electric car, which will be coming in a year or two. I mean, they're going to flood on the market this year, really. Can we do it for a ship? Well, I think that there's a lot of work to be done, but I can't see in principle why we shouldn't. What the cars did is they have their backbone system, which is like a motorway along which signals are conducted, and you can simply plug any system you develop into this backbone, and the communication is by issuing signals which are picked up by other systems in the backbone. The propulsion system, the auxiliaries, the auxiliary machinery, the ballast and trim, navigation, cargo handling, information communications maintenance, they all need to work they all need to communicate with each other. And of course, we've also got sensors around the ship, and we've got the electronic control units. Each of these systems will need to be built and designed with its own electronic control unit, but that control unit needs to be able to communicate with others through the CANBUS system. And the big issue here is arbitration. If you're pouring messages into this backbone, you need a very clear, robust system for ensuring that the most important messages get delivered, and that that messages don't just disappear. And that's what the CANBUS, that's what the backbone does. And the latest system is CANBUS F2, but there are other ways of doing this. And of course, like your motor car, you might like your OBD2 port that you just plug an information system into and you get all your diagnostics. Okay, so what we want to do is develop a world fleet 2020 to 50. We've got a 3-step strategy with no replacement for the diesel engine in place at the moment. I think what we need to do in step 1, this is the million deadweight of ships. Step 1, we fine-tune the existing diesel ships and start to introduce the digital technology I've been talking about as much as we can. And then we move forward to the next stage where we have, other types of fuels, possibly fossil fuels. I've put LNG here, but it could be anything. And of course, you're also using hybrid and battery systems and whatever semi-clever technology has come up and is available by the mid-2020s and can be used. And they will start. And then finally, the electric ships. People tell me that we might have some sort of electric system where the fuel cell or some sort of internal combustion system. I have no idea. I mean, but by 2030 that might be possible. And so basically we have a system that looks rather like the system that was used to develop the steam engine, and the whole thing takes over a century, in fact. The final thing really is how the companies operate. We have this opportunity to have a fleet of ships here linked and communicating via their their systems, and they communicate through microservices with their warehouse on the cloud, with the people they do business with, equipment suppliers, customers, ports. They use satellites, but they also use land-based Wi-Fi where it's more cost effective. And then, of course, we build in the shipping company with its management systems and dashboards. These companies are likely to have a lot more people working away on their systems and doing all these jobs here, the advisory, regulatory, fleet performance, data value accounting, new personnel systems. And I think this will create a terrific opportunity for sort of rotating the personnel around this system so that people do a bit on the ship, a bit in the office, a bit in the management, somewhat, why not have technical people do a stint on the ship? I think that's the sort of future we're looking at. And so the whole of the business works together as one entity, as a transport factory, using the miracle of I4 technology. And that's where you get your really big gains and your massive savings, because your quality assurance systems start to work. And if you can get anytime you get quality assurance systems to work, you save 30%. Don't ask me why, but it seems to be a rule of thumb. Well, the conclusion is that in the decades ahead, the maritime industry faces 6 challenges. We've got to meet IMO carbon emissions door to door. We've got to focus on increasing the value of sea transport rather than just the volume. We've got to fine-tune existing designs while developing zero carbon propulsion. We've got to focus on integrating ship systems so that they can communicate robustly, for example, using CANBUS F2 or something like that. We need to develop sea transport factories that will be radically different in terms of the way they operate, their quality standards, their maintenance standards, and their personnel and organisation systems. And finally, the professionals in the industry, and I guess Marina is right at the heart of this, will need to provide the answers to vital technical questions for ship owners and shipbuilders. And those were the words that were used when RENA was set up in 1860. Well, that's it, guys. Thank you very much for your attention and for listening. I really appreciate it, and I hope this has been some little bit of help to you. Thank you so much. Bye now.